Today we're going to talk about sections 2.4 through 2.6. Okay. So first we have this process creation hierarchy. It's a graphical representation of the dynamically changing parent-child relationships among all processes. This creation hierarchy changes each time a process is created or destroyed. So let's go through this. Okay, so the root is always the top level process, and then the different OS processes, like the processes the OS does to help serve like our applications and things like that, are at level 1. And then, let's go here so you can also see this. In some operating systems, user processes are going to become under this ancestor of the root called init. This is only in Unix. Okay, so that's where the user processes goes. In other languages, the user processes might be directly under the root, but this is what we've got. Okay, so we're going to follow that example. So then each user that logs in will be, their parent process will be init. And then we have different applications that the users are using. And then each application can also have its own processes if there's several things application's doing. So when a process is destroyed, we're wondering, what do we do with the destroyed process's children? So there's different things to do. You could just basically destroy all this in memory, like right over it, or we could have the init process actually be in charge of that in case maybe it's running, it needs to finish, then init will take care of it until it finishes. Okay, so let's go through these questions here. A process at level I in the process creation hierarchy can have how many links to processes at the next higher level? And we are going to say 1. And that's because, except for the root, every process has exactly one parent process, right? So that's only one parent. A newly created process that's still in new at level I can have how many links to processes at level I plus 1? Okay, we're going to say 0. Why? Because child processes are created at runtime. So if we're new, we haven't actually been able to run on the CPU, and so no children could be created. Okay. Each link in the process creation hierarchy corresponds to a pointer directed toward the root, a pointer directed away from the root, or bidirectional. So it's going to be bidirectional. Both directions must be represented so any process can reach the parent and vice versa. So the children can reach the parent and the parent can reach the children. Okay, when the currently running process initiates the creation of a child process, the OS executes a create process function called create. This process function allocates a new process control block, and it fills the process control block with the initial values and links the process control block to other data structures. So what happens here is when the new process control block is allocated, it's uniquely identified by a pointer or an array index P. And then all of these fields, the CPU state memory, scheduling information, and accounting information are fields. And these are usually parameters. And then assuming that we only have 3 states, running, ready, and blocked, those are going to be set to ready. The parent field of P is set to point to itself because the P is calling itself, basically. The P is calling something to make a child. So like in the case of like the parent being the root, then the root is making a child, like it could be, an operating system process or a init, okay, in that instance. In turn, P is inserted into the calling process's list of children as a new child. Okay, so this is basically, we're saying it's a process that's creating a child, and so that child will be P. The remaining fields are set to null because when we are in state of ready, there's no children, no open files, no other resources. P is inserted into the ready list. It's ready to be put on the CPU. The scheduler function is called to select the process to run. Depending on the priorities of the two processes, the scheduler could choose to start the new child process P or to continue the execution of P's parent process. So here we are basically, you can kind of clearly see we're sending in, the CPU state, the memory, the scheduling information, the accounting information, here we're setting everything. And then we call the scheduler to see if should we run this new child we created, or keep running the parent. And that depends on whatever scheduler we're going to use. Okay. The create function fills the various fields of P's process control blocks from different sources. Identify the correct source for each sample field. Okay. The parent, let's see. Let's go with open files. There's no open files because we're going to be in new, so that's going to be null. The memory is going to be a input parameter. The process state could just be a constant value like 0, 1, and 2 for running, ready, or blocked, or if you have more than that, it could be those. And then parent will be a pointer. Okay. So we have a new process control block. Since P has not run yet, the initial CPU state is null or undefined, true or false. It would be true. False. Sorry. Okay. Because the program counter must be set to the starting address, and the stack pointers must be set to point to the top of the stack. Sorry. Brain fart. Okay. The initial value of the process state field could be set to block if memory or some other critical resource is unavailable. True or false? A process only enters block state when it's running, so that's not going to happen. Okay. The scheduler function could choose a process other than P or P's parent to run next. The priority of P's parent didn't change, and neither did the priority of the other processes, so they're not going to change. Okay, process destruction. A process P can be terminated by the parent process by calling the function destroy. Also, completing the work or committing a fatal error results in the process destruction. The destroy process function destroys a process by freeing the data structure of the process control block and removing any references from the system. Depending on the OS, the destroy function may also destroy all the process's descendants to prevent having orphan processes. And so we would call that destroy recursively for all the children. So these are the steps, and we've got them down here in the pseudocode. After calling destroy on all child processes, remove P from the ready list or the waiting list. Release all memory and other resources, close all open files, and deallocate the process control block. Call the scheduler to select the next process to run. This call has to be made outside of destroy function to guarantee that the scheduler executes only once. Otherwise, it could be recursively called by all the children. So if you've got a lot of children and you were calling it in this block, that could be a problem. Okay, so when a process is destroyed, is it beneficial or detrimental that the children are recursively destroyed along with P? Okay, so we won't have orphan processes in that case. Is it beneficial that the children are assigned to a specialized OS process as a new parent? It could be beneficial because then they can, run until they're finished. The children would be left without a parent. Is that good or bad? Detrimental, because we could have runaway processes that could take over the OS, or at least take a lot of time from the the CPU. Okay, the responsibility to close all files should rest with the programmer, not the destroy function. A process can be destroyed at unpredictable times, and the programmer has no way of knowing when files would need to be closed. So that's why. And then we're going to skip the rest of these because I don't feel like they're useful. And we are in your welcome to look at exercise 2.4-1 for more clarification if you want. Okay, let's go to resources. Also, just wanted to make a point. We have PowerPoints. So if you want to use those, and it kind of highlights the main, part of what we're doing here instead of all of this text. So those are available on Blackboard. So the OS maintains numerous resources that processes can request and release at runtime. And we've talked about those resources. Most resources can be represented and handled uniformly using the same data structure and operations. So similar to a process control block, we're going to have a resource control block. And it's a data structure. It represents a resource. And so these can vary, but the basic thing you're going to have is a resource description, a state to say basically if it's available or not. So this can, if it's just one single unit, then this would be free or allocated. If it's multiple identical units, then it could be like an array or something like that. And then waiting list. The waiting list is basically for all the processes that request R. If R is busy, it puts them on the waiting list. So with a single unit resource, the state's just a Boolean. True. A waiting list is a linked list where each element points to a process control block. It could be, let's see, it can be, this is actually a little misleading. It could be represented in different ways. So we should say can be implemented. Okay. So our organization of resource control blocks. The set of all resource control blocks can be implemented in different ways depending on whether the number of resource control blocks is fixed or variable and whether all fields can be represented by only integers. Okay, so we have the number of resource control blocks is fixed. All fields contain only integers. What would be a better thing to have? I would say a 2D array of integers, right? Because it's fixed, so we can have an array, and it's only integers. The number of resource control blocks is variable, and all fields contain only integers. So a linked list, I would say, for the RCBs. So let's say this. The number of RCBs is fixed. Some fields contain values other than integers. So we could say an array of like objects or structures. I think they're thinking about C, but in Java we would do objects. And linked list of structures if the number of RCBs is variable and some fields contain values other than integers. If we want to request a resource is allocated to a process if the process has access to and is able to utilize that resource. A resource is free if the resource may be allocated to a requesting process. When the currently running process needs a resource, the OS executes a request function, and this request resource function allocates a resource R to a process P or blocks P if R is currently allocated to another process. So if R is free, the state of R is changed to allocated and a pointer to R is inserted into the list of other resources of P. Remember that field there. If R is not free, the calling process is blocked. P's process control block is moved from the ready list to the waiting list of R, the resource R. Since the calling process P is now blocked, the scheduler must be called to schedule another process to run. So here we have a request of R. If R is, and this is the actual process making this request. So if if the state of R is free, then we're going to say R is now allocated and then put it into the process's other resource list. Otherwise, we're going to say it's blocked and move it from the ready list to the waiting list, and then call the scheduler to see if another process can utilize the CPU. Okay, a process can be blocked on more than one resource. No, because when it's blocked, it can't do anything else. And so, yeah. A request can be initiated by any process regardless of the process's current state. No, because only a running process can initiate an action. Instead of blocking the calling process when the resource isn't available, the function could return immediately and let it continue executing. Yes, that's called a non-blocking call. Okay. So, releasing a resource. When the current running process P wishes to release a resource R, the OS executes what's called a release function. This release resource function allocates the resource to the next process on the waiting list. If the waiting list is empty, R is marked as free. So if R's waiting list contains no processes, then the state of R is changed to free and P continues executing. If the waiting list of R isn't empty, then the process queue at the beginning of the list is allocated R, the state of Q is changed to ready, and Q is moved from the waiting list to the ready list. Since a new process Q is now on the ready list, the scheduler must be called to decide which process P or Q should continue to run. So here's the pseudocode here. So we're going to, if we want to, release a resource, so the process is calling this, we remove that resource from the process's other resources list. And then if it's empty, there's nothing on the waiting list, then R is just free. But if there's something waiting to use R, like another process, Q, we remove process Q from the waiting list. We insert that resource into the other resources list of that process. We change the process state of that process Q to ready. We remove it from the waiting list, put it on the ready list, and then call the scheduler. So it might not necessarily be Q running next, but at least it's on the ready list. The release function always reactivates exactly one waiting process, 0 or more processes, or 0 or 1 process. Okay, so if there's nothing on the waiting list, it's going to be 0. If there's more than one, then we just grab the first one there, and so that would just be 1. We're going to skip 2.5.5 and 2.5.6. Okay, the scheduler. The scheduler function determines which process should run next and starts the process. The scheduler function is called at the end of each of the processes a resource management function. So we call the scheduler after we create, destroy, request, or release. Okay, create and destroy are from processes. Request and release are for resources. Okay, so these are different. But the scheduler is called each of these. Remember, if we want to create a child, destroy children, or destroy ourselves, or a process. Request is requesting a resource, release a resource. Okay, assuming the ready list implemented as a priority list, which isn't always, but we're assuming that for this, the scheduler function performs these tasks. We find the highest priority process Q on the ready list, and we perform a context switch from P to Q if either of these conditions is met. The priority of the running process P is less than Q. Okay? The state of the running process P is blocked. So here we're in pseudocode, we're finding the highest priority process Q on the ready list. If the priority P is less than Q or the process state is blocked, we're going to perform a context switch. What is context switch? Remember, that is where we basically, if like we're running P and we want to move it to the ready list, we take everything that's we have about P, that's in the CPU and all the registers, copy it into the process control block so we can have it next time we want to run P. Okay, 1 second. One more second. Okay, the calling process P could be preempted by some other process Q when the scheduler is called from create, true or false. It's going to be true. P could create Q with a higher priority. Destroy, true or false. It's going to be false. Destroy does not insert any new processes into the ready list, and so the ready list can't contain any process Q with priority higher than P. Request, true or false. True, because if P blocks, then some other process Q is resumed. Release, true or false. True. Release could unblock a process Q with a higher priority than P. Okay. If the ready list is implemented as a single list without priority levels, and every new process is entered at the tail of the ready list, then these functions don't need to call the scheduler. Create. It does not need to call the scheduler because the new process is inserted at the tail of the ready list. The calling process continues to run, and create doesn't need to call the scheduler. Destroy. True. As long as the process can't call destroy on itself, the process will continue to run. Request. False. When the resource isn't available, the calling process is blocked, and scheduler must be called. Release. True. The released resource is marked as free or is allocated to a waiting process, which is entered at the tail of the ready list. The calling process continues to run. Okay, you're free to look at those request and release functions in action exercise. It's kind of going to clarify if you need it. And so, yeah, but I'm going to go on to threads. Okay, an application implemented as a single process follows a single path of execution through a program. So whenever the execution blocks, if it's waiting for a resource to become available, the whole process blocks. And many applications have parts that can run concurrently if each could block independently. Also, if we had multiple CPUs, they could all run in these different parts could run in, independent parts could run on multiple CPUs. But creating a process for each of many short-lived activities, which potentially short-lived activities, is inefficient. And so a thread is an instance of executing a portion of a program within a process without incurring the overhead of creating and managing separate process control blocks. So here's some uses of threads. A browser could draw an image on the screen while at the same time waiting for data from the internet. That's why we see images kind of load a little bit at a time. That's what's happening. It's using threads. A word processor can run a spell checker at the same time as the user's typing. That's another one. So they're happening at the same time. Okay, so here we have a nice infographic. A single threaded process has a single program counter. The PC moves, this is the program counter, moves through the program as the execution progresses. A process with multiple threads has a separate program counter for each thread. The different program counters advance through the code independently from one another. When multiple CPUs are available, the threads can proceed in parallel. Multiple threads within a process will always execute the same sequence of instructions, must execute within disjoint parts of the program, may execute different sequences of instructions with any part of the shared program. That's true. Each thread is independent and can execute any sequence of instruction within the program regardless of any other thread. Using n threads within a single process is more efficient because the threads share the same code and data. Yes, the threads can take advantage of multiple CPUs. Both processes and threads can take advantage of multiple CPUs. That's kind of worded strangely. Sorry about that. Threads can block independently from one another. What do we think? Let me think about that. False. Both processes and threads can block independently from one another. So this is basically, it's a little confusing the way they have it worded because we're saying processes versus threads. So this one was false because processes and threads both can take advantage of multiple CPUs. And this is false because they can both. So that wording is pretty confusing there. Okay. Each thread is going to have a thread control block. I think we're starting to see a pattern here. So we're going to have a resource control, block, a process control block, and a thread control block. A thread control block is a data structure that holds a separate copy of the dynamically changing information necessary for a thread to execute independently. And what makes threads more efficient than processes is we're only replicating the bare minimum of information in each thread control block. But we're sharing the same code, the global data, the resources, and the open files. Okay, another nice infographic. A single threaded process has one program counter and one stack pointer. Remember, we can use stack pointers for like recursion. We have like stack. That's one use of a stack pointer. Also, when you're just calling different functions within each other, that's a stack pointer. Can be used for that. The process state may be running, ready, or blocked. The CPU state is replicated in each thread control block. So that's one of the few parts that's replicated, giving each thread control block a private program counter and stack pointer. The process state is replicated as a thread state in each thread control block. Thus, each thread can be running, ready, and blocked independently. Other fields, because they're shared, remain in the process control block. Each thread accesses the shared code using the private program counter. Each thread also has a private stack. Threads are faster to create and destroy than processes. True or false? True, because it's simpler data structure. In a multi-threaded process, the PCB is replaced by multiple TCBs. No, there's still one PCB and then multiple TCBs. Memory and other fields aren't replicated in the TCBs because the data is not needed by the threads. False, they need them, they just share. Okay. User level versus kernel level threads. So threads can be implemented completely within a user application. A thread library provides functions to create, destroy, schedule, and coordinate threads. The library maintains all thread control blocks within the user process. Consequently, the OS kernel isn't aware of the threads and treats the process as single-threaded. So the alternative is to implement threads within the kernel. The TCBs aren't directly accessible to the application, which uses kernel calls to create, destroy, and otherwise manipulate the threads. So those are two different things that we can have, user level or kernel level. So here, when the process starts running, the saved CPU state is copied into the CPU, and the CPU continues executing the code using the program counter and the stack pointer. The PCB is going to get out of date as the process executes. We know that. Using the thread library, The application can create multiple threads, each using a different program counter and stack pointer. All threads share the code and global data. Same, right? The thread library switches between the threads by saving and copying the CPU states between the TCBs and the CPU. With user-level threads, all thread management occurs within the process, the user process. The kernel doesn't know there's multiple threads. With kernel-level threads, this management is handled by the kernel using internal thread functions. The application uses kernel calls to request an action. With a multi-threaded process, a context switch between threads is performed by the kernel. Only with kernel-level threads. User-level threads, the kernel has no idea they exist. Okay. With a multi-threaded process, each thread control block maintains a separate copy of the thread state, but the process control block must also have a copy of the process state. What do we think there? Let's go with this one. The kernel is aware of only the process control block, not the individual TCBs, and thus can only keep track of the process state. The individual thread states are manipulated by the thread library. So there's advantages of user-level threads over kernel-level. Because user-level threads don't require any cooperation, they're usually faster to manage. An application using these are more portable between different OSs without modifications. However, there are disadvantages of user-level threads over kernel-level threads. They're not visible to the kernel. When one blocks, the entire process blocks, which decreases concurrency and then can decrease performance and responsiveness of an application. User-level threads cannot take advantage of multiple CPUs because the process is perceived by the kernel as a single thread. So many modern OSs take a combined approach. The kernel supports a small number of kernel-level threads. Each application can implement any number of user-level threads, which are then mapped onto the KLTs based on the needs and the available resources of the user-level threads. So let's look at this combined approach. The kernel is going to maintain a small number of kernel-level threads, and the kernel is going to schedule those on available CPUs. Each process can create any number of user-level threads using a thread library. The programmer will decide which user-level thread or groups of user-level threads are mapped onto different kernel-level threads. When U1 blocks, K1 blocks as well, but as long as at least one of U2, U3, or U4 is running, the process continues running in K2. When U1 runs again and one of U2, U3, or U4 continues running, then the process may continue in parallel. Okay. A process consisting of n user-level threads is to be mapped onto a set of m KLTs. Which combination wouldn't be useful? Okay. So the m, so we would need more kernel-level threads than user-level threads, and we would want to have both of these be more than one. So the N ULTs could not utilize all the M KLTs since each ULT is sequential. Kernel calls are blank to manage thread, needed only with kernel-level threads, needed only with user-level threads, always needed never. They're only used with kernel-level threads. Okay, and we have some exercises here that you're free to look at, and that is it.